Segment 22B, the solar magnetic field. In this segment, we'll discuss sunspots and the solar magnetic field and the Earth-Sun interactions that result from magnetic effects in the Sun. As we mentioned in the last part of this segment, the solar photosphere is a layer within the gas where the Sun becomes opaque as we look at it. When you look at the photosphere, one of the most dominating features is the presence in the equatorial zone of sunspots, what appear to be very dark spots moving across the surface of the Sun as it rotates. When you look at these more closely, they have a lot of structures to them. But one of the questions you want to ask is, why do they look dark? The answer is they're not dark at all. They're actually very bright. However, they're a few hundred degrees cooler than the rest of the surface of the Sun. And because of the blackbody rules, cooler objects radiate less at all wavelengths than bright objects. They appear fainter than the rest of the Sun. And given how the tremendous amount of energy that's coming out and the very high temperatures involved, this contrast results from just a minor difference in the temperature. The spots that you're looking at here are thousands of miles across. Now, one of the things about sunspots is they're easy to observe, and as soon as Galileo had discovered the sunspots, people started to monitor them, and we have records of sunspot frequency because they're easy enough just to count, going back for hundreds of years. And it's been known for a long time that sunspot number counts follow an 11-year cycle where there's a maximum approximately every 11 years, although the number in any given maximum may differ rather radically. Sunspots in the sunspot cycle are manifestations of magnetic activity on the Sun. Observations of Zeeman splitting in sunspots demonstrate the strength and organization of the magnetic field. So this is a lot of scientific jargon. What it is that there are certain spectral lines of different atoms who are sensitive to the presence of a magnetic field, and when the magnetic field comes along, and you can demonstrate this in the laboratory, the lines split into individual components. So you're seeing here on the left a sunspot and the slit of a spectrograph put across that sunspot, and on the right the spectral lines displayed. And you'll notice that the left-hand line in the green plot doesn't change very much, but those lines in the middle are outside of the sunspot. In the normal Sun, it's a single line, but when you get into the Sun, it splits up into three separate lines. This is the result of the magnetic field's effect on the atomic transitions, on the energy levels within the atom itself. And this effect is demonstrable in the lab and is very well understood. It allows you to measure the strength and the organization of the magnetic field in the Sun. With this knowledge, we've been able to understand a lot of what's going on. So here, for example, you see arches and loops of glowing gas above the solar surface that are then taken in photographs with special filters that are in lines that are sensitive to the temperature of gas that would be present in these loops. But you see this very fine structure. That's the magnetic field emerging from the solar surface at one sunspot, going back into the solar surface at another sunspot. So how does this come about? Well, it turns out that the Sun does not rotate as a solid body. It's made of gas, and in fact it rotates more quickly at the equator than it does farther up. And this differential rotation and the fact that the magnetic field is trapped by the ionized gas inside the Sun tends to wind up the magnetic field. The magnetic field gets bent more and more and more and more, and eventually some of the field lines will pop out of the surface of the Sun, and that's when you get a sunspot. And the solar cycle is due to the fact that every so often the Sun's magnetic field has to readjust itself. The tension on these field lines becomes too large, and the Sun has to readjust, and the field reorganizes, and the whole activity cycle then starts over again. Many interesting solar phenomena are due to this magnetic activity. One of the most exciting are the solar flares, where you get an event where there's a sudden change in the magnetic field that leads to an acceleration of a large amount of gas out of the solar surface, and this gas gets heated to very high temperatures and flies out. This sends energetic particles out in the solar wind as a burst of gas that happens at one of these flare events. And these flare events are very important to us here on the Earth because they have a strong effect locally. The particles that fly out at a few hundred kilometers a second, particularly the electrons, wind up being caught by the Earth's magnetic field. So here you see a solar storm. This is now a flare event that's leading to an ejection of a large amount of material along lines coming out from this sun's surface. So, and this is another picture where we block the photosphere of the sun in order to be able to see this emission coming out. This is done with an artificial disk, not with during an eclipse, because people wanted to look at this particular set of flares. And one of the most noticeable phenomena that comes from this is the Aurora Borealis. When these high energy particles are trapped by the Earth's magnetic field, some of them move along the field lines, and the field lines from the Earth's field enter the Earth's atmosphere at the north and south magnetic poles. And when these energetic particles hit the upper part of the atmosphere, they excite the oxygen molecules that glow in this unearthly greenish color, and that's what causes the shimmering northern lights. Unfortunately, they also cause disruptions in low frequency communications, and while now our cell phones and things like that are not heavily disrupted, these are the kind of communications that are used, for example, to communicate with nuclear submarines, and so it's an area which is of great interest for military reasons.